As you learned in the background information, there are 4 gas laws that describe the proportions within gases. When all of these laws are combined, the resulting proportion is as shown. In order to convert from a proportion to an equation, a constant must be added. This constant is known as the universal gas constant. Remember from Avogadro's law that 1 mole of any gas will occupy 22.4 liters of volume at STP, which is 1 atmosphere pressure and 273 Kelvin. Now we can incorporate this theorem in order to find a value for R, the universal gas constant. If we solve for R and plug in all the values, R equals 0.0821 atmosphere liters per mole Kelvin. The units of R are important since using different units for pressure, temperature, and volume will result in a different R value. The ideal gas law can, as the name states, only be applied to ideal gases and theoretical situations. This is due to the physics aspect of the ideal gas law, the kinetic molecular theory of gases. This theory states that a gas is ideal if and only if these following 6 conditions apply. The particles must behave like hard, spherical objects in random, constant motion. The particles must follow straight line paths. Most of the volume in the container must be empty space. There may be no force of attraction within the gas. Collisions among gas particles must be perfectly elastic, and the kinetic energy of particles may only vary with temperature. If these conditions are true, the ideal gas law may be applied. Real gases act most like ideal gases when they are contained at high temperatures and low pressures. In 1873, a scientist named Johannes van der Waals won the Nobel Prize for deriving an equation that makes up for all of the conditions and can be used for any real gas. This equation, while useful, involves mostly very advanced physics and is specific for each gas, so it isn't taught in high school courses. Okay, now pause the video and try to do this problem on your own. Okay, so from the given information in the problem, you know that you have 0.25 molar chloride ions, and to find the number of moles, you multiply that by the volume of the sample, which is 0.025 liters, and you get 6.25 times 10 to the negative 3 moles of chloride ions. To solve for the volume of chlorine gas, you first have to multiply the number of chloride ions there are by 2, so the number of moles by 2. And that's how you get the number of moles of chlorine gas. And you get 3.125 times 10 to the negative 3 moles of chlorine gas. Then you plug this number into the ideal gas formula using the other given information to solve for the rest of the variables. So when solving for volume, you say 3.125 times 10 to negative third, whoops, I forgot that, times 10 to negative 3 moles of chlorine gas times 0.0821 liter atmosphere over Kelvin mole times 295 Kelvin all over 0.95 ATM. And when you use those numbers, you get volume equals 0.0797 liters. Yay!